Hi guys, today we will learn about surface phenomena. So for this lecture, the student is expected to understand and able to explain about surface energy as well as surface tensions. Okay, and you are also expected to understand interfacial tension and able to explain on the application of surface phenomena in pharmaceutical application. So to explain about surface energy, let us look at the two-dimensional atoms here. So we have the first case where the atoms are arranged in square shape, okay, and under a certain force, okay, the shape become rectangular. Okay, so what is the surface energy of the solid when the atoms are arranged in the square shape, and what are the surface energy of the atom when they are arranged in a rectangular shapes? So let us look at the atom one by one. So here we have the same 56 atoms. Okay, so for the first case, in the 56 atoms we have 30 saturated atom. So saturated atom means the atom that being bound in all directions. So the atom in the middle, so they are being bound by this atom here, here, okay, here, okay, is what you call a saturated atoms. Okay, so here you have 30 saturated atoms and 26 unsaturated atoms. So who are the 26 unsaturated one? So those reside on the surface of this square are atoms that are unsaturated. Okay, so we have 30 saturated and 26 unsaturated atoms. So what are the total bonds? Total bonds in this square shape of atoms. So let's look at, to bind one atom to another, we have one bond. All right, so here we have how many bonds that we have now? 1, here 2, here 3, here 4, 5, and 6. So we have 6 bonds, and let us define the bond as B. Okay, the force of the bond is B, and when we have 6 atoms, so we have the surface force of 6B. So what is the total force acting vertically? All right, vertically to the square. Okay, let's say we know that one bond between atom is B. So the force act vertically to the square is the one here that you can draw a line down vertically. Okay, and you know here is B, okay, and here is half B. So let's say the vertical force is C. So what is C? Okay, so if you look at the triangle here, it is a, you can use theorem Pythagoras to sort out C. So C is equals to, so C square, we should say, is equals to B square minus half of B square. Alright, so when you have B square minus half of B square, it will be equals to B square minus 1 over 4 b squared. Alright, it will be equals to 3 over 4 b squared, and also is equals to square root of 3 over 2b. Okay, so c is equals to square root of 3 over 2b. So what is the total vertical force? Total vertical force acting on the surface of the square. So total vertical force will be equals to, so we have how many bonds, how many C here? We have 1, 2, 3, 4, 5, 6, and 7. So we have 7 C, so it equals to 7 times square root of 3 over 2 b. So to calculate the total surface energy of this material here, it will be equals to the perimeter of the matter. Alright, so what are the perimeter? The perimeter will be 2 times 6b plus, okay, 2 times 7 times square root 3 over 2b. Okay, then you can calculate the total surface area for the atoms in the square shape. So what happened to the atoms in the square shape when they change their shape into a rectangular via a certain force? Okay, so what is the total surface energy of the matter in rectangular? It will be again the perimeter of it. So what are the perimeter? Will be 13b times 2 plus, okay, plus this one, 3 times square root of 3 over 2b times 2. Okay, then you will have the total bond. So what are the total bond? Can you please calculate? Okay, so the total bond will be 31.2 b, and the total bonds here will be 21.4 b. Okay, given that both situation that they have the same amount of atom, which is 58 total atom. Okay, by just changing the shape via a force, then the surface force of this material has changed. This is what associated by surface energy. So in this slide, I present the true calculation for area per unit of these metals, which is 21.4 b. Else for here is 31.2 b. So when you change from the square shape to the rectangular, there is energy associated with creating surface. Okay, so to make more surface, we have to break the bond, which means that work has to be done, and this is what you call surface energy. So to define surface energy clearly, surface energy is the work per unit area that done by the force to create a new surface. So looking at this picture, when you have different atoms in a matter, okay, and the atom in the middle is being bound by the adjacent atoms. Okay, so for example, the middle atoms is bound through 1, 2, 3, 4, 5, 6, 7, 8 bonds. Okay, and what happened to the atoms on the surface? Okay, atom on the surface only bound by 1, 2, 3, 4, 5 bonds. Okay, so there's imbalance bond experienced by the atom on the surface as compared to the atom in the bulk. So there is a net effect is that the molecule at the surface of the liquid may experience an inward force towards the bulk, because in the bulk there is higher forces involved in the bulk. That's why whatever the experience on the surface, there is a net effect of inward force. So there is a tendency to contract, okay, and this create a force on the surface that they try to minimize their own areas, and by minimizing this area, it is accompanied by a decrease in surface free energy. Okay, this is that give the surface different characteristic from the bulk and give rise to surface tension and surface free energy. So when we consider the force, okay, rather than energy, then the term is called surface tension. And when we consider it is as an energy, then it is surface energy. So surface tension can be seen in our daily life. If you notice, some insects can walk on the surface of water. Okay, this is some examples. And when you have a very tiny clip, even though you have a high density, but they can still float on the water. This is because of surface tension. The surface tension is a result of different forces experienced by the molecule in the bulk as compared to the molecule on the surface. Here we have others example. Okay, so when we use water in this petri dish and alcohol in another petri dish, okay, and we try to put a blade on top of the water, the blade will float on the water. However, it doesn't float on the alcohol. Okay. So even though they're trying to put it carefully on top of the alcohol, it seems that it doesn't resist and it will sink in the alcohol and float on the surface of water. However, a few drops of alcohol, if added to the water, the blade will sink. Same happened to this scenario. When the blade is placed carefully on top of the water, the blade is floating. Okay, even though it has higher density. Same goes to the needle. Okay. However, when there is small an amount of detergent that can break the surface tension of water is added to the water, it can break the surface tension and both items will sink at the bottom of the container.
Observe the sewing needle placed on the surface of water and an insect walking on the surface of water. We observe that the sewing needle, which is denser than water, floats on it. and the insect is able to walk on the surface of water. How is this possible? This is because free surface of water, which is at rest, behaves like a stretched elastic membrane supporting the needle and the insect. This property of liquid is known as surface tension. Thus, surface tension can be defined as the property of matter by virtue of which the free surface of the liquid at rest behaves like a stretched elastic membrane having contractive tendency. Let us now study this property of liquid in terms of molecular force of attraction. Consider three molecules, A, B and C, of a liquid. The dotted circle drawn around each molecule represents the sphere of action of each molecule. Observe that the sphere of influence of the molecule A is completely inside the liquid. It is attracted equally in all directions by the other molecules. There is no resultant force acting on the molecule A. The molecule B, that is closer to A, also does not experience resultant force. What about molecule C? A part of the sphere of action is above the liquid surface. The molecule C experiences a resultant downward force. Now consider the molecule D that lies on the liquid surface. This molecule has its sphere of action exactly half outside the liquid and half inside the liquid. Thus, the molecule D experiences a downward attractive force. Due to this downward attractive force, the molecules on the surface experience a tension called surface tension.
So to define surface tension, definition of surface tension is the force per unit length that must be applied parallel to the surface so as to counterbalance the net inward pull. And this force has the unit of Di per cm, okay, in the CGS system, and they can also carry Newton meter in the SI system. So since we have learned about the surface tension is a result of the forces between the molecule, imbalance forces between molecule, okay, forces between the molecule in the bulk as well as molecule on the surface, okay. And when we talk about the same molecule, it will be cohesive force. Alright, okay, tell me, when the cohesive force between the molecule of a liquid become greater, what happened to the surface tension? Okay, we shall discuss in our lecture. Okay, mathematically, we can understand surface tension and surface energy by using drop weight approach. Drop weight method. Alright, so in this method here we have two wire, okay, with a slider here, okay, and this is the end of the wire as well. Alright, and we try to make a soap film here. Alright, and the slider is attached to a weight, okay, and this certain weight will actually draw the film soap to a bigger area, okay, and here we can calculate surface tension of the film, okay, because when we talk about the force it will be surface tension, but when we talk about the surface free energy, then it will be work done to increase the surface area, so it will be surface free energy. Alright, but however we are talking about the force, okay, here, so we look at the surface tension of the film. So here are the explanation of the drop weight methods. You can read about it. Okay, so when we have the weight here that they can draw the film into a bigger area, okay, let's say there's this force F. So what are the surface tension? So surface tension will be equals to the force per unit length, right, that is generated by this weight. So however the length, it should be here, right, here, and we have the wire have two surface, one at front here and one behind, so we have 2L, okay, so surface tension is equals to the force divided by 2L. Okay, so how you define F? So in form 5, I guess you learn about F equals to ma, right, equals to ma. However, the A here in this case is drop weight method, so the A is gravity over 2L. So your surface tension is equals to mg over 2L. Okay. Okay, now let us look at this example. If the length of the bar L, which is here, is 5 cm and the mass required to break a soap film is 0.5 gram, here 0.5 gram, what is the surface tension of the soap solution? Okay, of course, if you still remember our previous slide, the surface tension can be determined by using the force per unit length, and here the length will be the one in front and the one behind, because there's two surface, one surface from here and one surface from the front. Okay, so two surfaces, so will be F divided by 2L. So what is F? F is equal to ma divided by 2L. In this case will be mg divided by 2L. So what is m? Is 0.5. What is g? 981. And what is L? Is 5. So you can actually solve this question. So what is the work required in this example to pull the wire down 1 cm as shown in the figure? Okay, what is the work required? Then you will need to convert into energy. So here is the answer for surface tension, which is equals to 49 dyne per cm. Okay, so if you are asked what is the work required in this example, so work requires will be equals to, okay, because the area is increased by 10 centimeter square, so the work done is 49 times 10, which is 490 ERGS. Okay, if you need to calculate using the SI unit, then you may actually convert by using the equation here. So up to this point, I hope you understand and able to explain about surface energy and surface tension. And now let us go into the interfacial tension.
We'll need to go back and review Chemistry 101. You probably all remember that big chart that hung on the wall of the high school science lab. It's the periodic table, a cheat sheet of sorts, that categorizes all the unique atoms or elements that make up matter: hydrogen, sodium, carbon, nitrogen, oxygen. Now you will recall that when atoms combine, they form molecules. For instance, when an oxygen atom bonds with two hydrogen atoms, it creates the molecule H2O, or water. You'll notice the structure of the molecule. The oxygen atom has an excess of electrons and is negatively charged. The hydrogen atoms have fewer electrons, and they are positively charged. The molecule has poles, much like those on our planet. And these poles make the molecule polar. Molecules with a more equal distribution of electrons simply cancel each other out and are nonpolar. And this is important because polarity affects solubility, the ability of two substances to mix. So if we mix polar H2O molecules with other polar molecules, let's use ethanol, the two substances mix. The alcohol is soluble in water, and nature likes this combination. You see, polar molecules like to be with other polar molecules. But if we go back to our periodic table and we make a nonpolar molecule, like cooking oil, and then we mix our oil molecules with our water molecules, and I'm sure you know where this is going. Oil and water don't mix. Nature doesn't like this combination. Nonpolar molecules only like to mix with other nonpolar molecules. They may temporarily disperse, but the oil molecules stick together and the water molecules stick together. And given a little time, all of the like molecules will find each other.
So interface is the boundary between two or more phases exist together. For example, when phases exist together, the boundary between them is termed as an interface. So when you have gas and gas, there's no interface possible. When you have gas and liquid, usually we will call them surface tension, okay? Or you can say it's interface between liquid and gas, okay? When you have gas and solid, that will be solid surface. Liquid to liquid will be liquid to liquid interface, liquid to solid interface, and solid to solid interface when you talk about the powder mixture. So interfacial tension is the force per unit length exists at the surface interface between two immiscible phases and has the unit of dyne per cm, which is similar to surface tension. This is because even though surface tension is an interface between gas and liquid, okay, and it has to be immiscible, then only you have interface, and then only you will have the tension. And it is most often used for attractive force between two immiscible liquids, two solid, and at the liquid solid interface. And interfacial tension of organic solvent and water will be lower than the surface tension of water itself. Surface tension of water will be, you have to remember this value, 72.8 dyne per cm. Okay, if two liquids are completely miscible when there's no interfacial tension, so there's no interfacial tension between them. So here are some examples of interfacial tensions. So when you have water only, the surface tension of water is 72. Please remember this number. Okay, and glycerol, they have a surface tension of 63, and oleic acid surface tension of 33, but their interfacial tension with water will be 16. Okay, and benzene, surface tension is 29 and the interfacial tension is 35. Okay, and chloroform interfacial tension with water is 33, 8.5, 45, 33, 51, and 11. And if you notice, interfacial tensions between the organic solvent themselves, all right, of course between organic solvent themselves is their own surface tension, and when they have the interfacial tension with water, it will be always lower than the surface tension of pure water, because pure water has always the very high surface tension, which is 72. And please remember this number. So question, if two liquids are completely miscible, A, interfacial tension is negative, B, interfacial tension is positive, C, there will be no interfacial tension exist between them. So please choose your answer. Okay, lastly, let us go into the application of surface phenomena in pharmaceutical. Okay. And why you need to know about surface phenomena? It is because interfacial phenomena play an important role in the processing of a wide variety of formulation, for example, tableting. And you have different dosage form, for example, emulsions and colloid, which is involve the knowledge of surface chemistry. Okay, and suspension, where you need to disperse the solid in a liquid phase. Okay, and surface tension is also very important for drug performance when it relates very well into the wettability of the dosage form. So wettability is how much the water can be wet before they dissolve. Okay, and the drug need to be completely dissolved, okay, and become molecule before they can be absorbed to the biological system. So the wettability will be the first step of dissolution. That's why it is very important that you have to know about surface phenomena of your dosage form. And also it is very important for the penetration of molecule through biological membrane, because if you remember in your first year you learn about biological membrane, which consists of phospholipid. All right, and phospholipid is a compound that they are amphiphile, which they have the polar head and the non-polar tail. Okay, in that sense they are a kind of surface active agent, and how they affect the penetration of molecule through this membrane. Okay, with that I think I end your first lecture.